Hello, my name is Peyton Heath, and this is my periodic motion lab on the physics of extreme sports with ropes. In this video lab report, I will begin by introducing the purpose of the lab, as well as the results produced by the lab. Then, I will explain the content model, followed by an analysis of the data it produced. Finally, I will go over the discussion questions and give a conclusion. The purpose of this lab is to produce a model that mimics the motion of a person bungee jumping, and to use this model to show that bungee jumping is governed by Newton's second law and the principles of simple harmonic motion. According to Newton's second law, the net force is equal to mass times acceleration. In addition, Hooke's law says that force equals the negative spring constant times the distance that the spring is stretched. From these two equations, we can derive a second-order differential equation, which we can use to find a vertical and horizontal position equation to fit the model. Although we cannot directly integrate this equation, we can use a guess and check method to find a position equation for the model. We know that a spring mass or a pendulum mass system oscillates like a sine or cosine wave. Thus, our position equation will include a sine or cosine function. When we use the guess and check method, we find that position is equal to a cosine omega t or a sine omega t, in which a is the amplitude of the wave and omega is 2 pi times the frequency. As a result of this lab, I found that the motion of the mass in the x direction and in the y direction follows Newton's second law. In both directions, the model exhibits simple harmonic motion. The period of the model swings in the x direction was approximately 1.23 seconds, and the theoretical period is 1.30 seconds. There is a 5.541% difference between these values. The period of the model's oscillations in the y direction was approximately 0.6 seconds, and the theoretical period is 0.628 seconds. There is a 4.560% difference between these values. A person bungee jumping swings back and forth like a pendulum while also oscillating up and down on the stretchy rope like a spring. Thus, our model needed to include both a pendulum mass system and a spring mass system. In order to accomplish this, we attached a spring to a pendulum mount and hung a mass at the other end. Then, we pulled the spring down at an angle and released it to cause horizontal and vertical displacement. In our model, the length of the spring was 0.42 meters, and the spring constant was 25 newtons per meter. The mass on the end of the spring was 0.25 kilograms. We recorded the motion of the model and imported it into the tracker software. Using AutoTracker, we collected data about the horizontal and vertical positions of the mass at various points in time. After Tracker generated the dataset, I imported it into Excel. In order to create the x position graph, I plotted the x-coordinate of the mass versus time. This graph shows the swinging of the pendulum. Using this graph, I created an equation for the x position of the mass. To do this, I used the first two cycles of the wave because they were the most consistent. Based on my data, I estimated that the amplitude of the wave was 0.15 meters and that the period was 1.23 seconds. Then, I calculated the angular velocity to be 2 pi divided by 1.23. I chose cosine as the best fit for my data because the wave is at a minimum when time is 0. Based on this information, I found the horizontal position equation to be x of t equals 0.15 cosine of 2 pi over 1.23 times t. Next, I created the y position graph by plotting the y-coordinate of the mass versus time. This graph shows the oscillation of the mass on the spring. Using this graph, I created an equation for the y position of the mass. The wave for the y position was more irregular than the wave for the x position. Since the final 3 cycles were the most consistent, I based my vertical position equation on those. Using my data, I estimated that the amplitude of the wave was 0.05 meters and that the period was 0.6 seconds. I calculated the angular velocity to be 2 pi divided by 0.6. Once again, a cosine curve was the best fit for my graph. Based on this information, I found the vertical position equation to be y of t equals 0.05 cosine 2 pi over 0.6 t. How do these equations of motions relate to the known equations governing harmonic motion? In our model, the spring oscillates up and down, and the pendulum oscillates side to side. Because it is oscillating, the lines of best fit for the horizontal and the vertical motion of the mass will be a sine or a cosine curve. The equations governing harmonic motion are also sine or cosine curves. Knowing that force equals ma equals negative kx, you can find that d squared x over dt squared equals negative k over m times x. When you use the guess and check method, you find that the position equation in the harmonic motion is x of t equals a cosine omega t or a sine omega t, which fits our model. Thus, the motion of the mass in our model is governed by simple harmonic motion. How can you reconcile these equations with the known formulas for calculating periods of mass spring or mass pendulum systems? The known formula for the period of a spring is 2 pi times the square root of m over k, and the formula for the period of a pendulum is 2 pi times the square root of L over g. The general form for the motion of a mass pendulum or a mass spring system is x of t equals a cosine omega t or a sine omega t, in which omega is the square root of k over m for a spring or the square root of g over L for a pendulum. Thus, you can use the position equation to determine the period of the spring or the pendulum by dividing 2 pi by the angular velocity from the equation to find the period. By doing so, you can compare the period given by the equation to the period given by the formulas for calculating the period. Comparing the oscillation periods. What does it mean? From the raw data produced by the model, I estimated the period of the pendulum mass system to be 1.23 seconds. Using the formula for the period of a pendulum, I found that the period of the horizontal motion was 1.3001 seconds. The percent difference between these two values is 5.541%. This percent difference is small enough to show that the pendulum mass system is in simple harmonic motion. From the raw data produced by the model, I estimated the period of the spring mass system to be 0.6 seconds. Using the formula for the period of a spring, I found that the period in the vertical direction was 0.628 seconds. The percent difference between these two values is 4.560%. This percent difference is small enough to show that the spring mass system is in simple harmonic motion. In conclusion, the motion of bungee jumping is governed by Newton's second law and harmonic motion, as demonstrated by our model. There was only a 5.541% difference between the model's horizontal period and the theoretical horizontal period, and a 4.560% difference between the model's vertical period and the theoretical vertical period. This difference could be the result of several sources of error. First, the length of the spring was not constant, which would have affected the value produced by the known formula for the period of a pendulum. Second, the mass of the spring was not taken into account, which would have affected the value produced by the known formula for the period of a spring. Finally, there could have been some error introduced by Tracker, which would have caused a degree of inexactness in my raw data. Thank you for your time. I hope you enjoyed this presentation.